This presentation will review the Alum Lab and discuss the steps and calculations necessary to finish the lab. Alum is known as potassium aluminum sulfate, and if you take a look at its formula, you will also notice that it is a hydrate, meaning that there are 12 waters in this case of hydration. And so when alum crystals form out of solution, as the crystals form, 12 water molecules are trapped as part of that structure. A recap of the lab. In step 1, we had the oxidation of aluminum. In this step, we combined approximately 0.5 grams of aluminum metal and added 25 milliliters of potassium hydroxide solution. If you take a look at this step in the equation, the aluminum ends up becoming dissolved when it becomes oxidized, and the potassium hydroxide provides a source of the potassium ions and also the hydroxide ions that are formed as part of the intermediate product, KAlOH4. In the next step, we'll see those hydroxide ions go away. In step 2, we are forming potassium aluminum sulfate, and to accomplish this, we added sulfuric acid solution. Sulfuric acid solution will neutralize the OHs in the KAlOH4 and also provide a source of sulfate ions in the product. In step 3, the precipitation of aluminum, we took the dissolved alum solution and placed it into an ice water bath. And those alum crystals will actually form in that ice water bath because the solubility of alum decreases as the temperature drops. And once we crystallized the alum and recovered the crystals, then we filtered them and recovered them using a Buchner funnel. And so the last step is really forming the alum, including the 12 waters of hydration as those crystals form. The questions that you need to answer are all the basic questions that are found throughout the lab procedure. In addition to those questions, make sure that you have included all your necessary observations and data, things like the initial mass of the aluminum, the mass of your filter paper, and the mass of the filter paper plus the alum at the end of the lab. Now, one of the tougher questions in the lab procedure is worded in this way. Combine equations 1, 2, and 3 to find a full molecular equation for the synthesis of alum. Notice that you will need to include equations 2 and 3 multiplied by a factor of 2 to properly cancel out the intermediate formed in step 1. So if you take a look at the equations that are numbered 1, 2, and 3, the molecular equations numbered throughout the lab, they are as follows. And I pulled these right from the lab handout. And it says that you will need to include equations 2 and 3 multiplied by a factor of 2. If you take a look at this first equation, and this intermediate potassium aluminum hydroxide is formed, but that's really not alum, and you'll see that that same product is then consumed or used up in equation 2. However, there's 2 moles of it in the first equation and only 1 mole of it in the second equation. So to get it to cancel out completely, we're going to have to multiply the entire second equation by 2. It also tells us that the third equation will need to be multiplied by 2 as well. So on the next slide, I have rewritten these equations, but multiplied equations 2 and 3 by a factor of 2. So the changes are shown in red. Now we're going to need to combine these equations to get a full molecular equation for the synthesis of alum. And as I take a look at the reaction, I should see several things that can be eliminated from the equation. The potassium aluminum hydroxide is formed in reaction 1 but used up in reaction 2. And likewise, the potassium aluminum sulfate, before it has taken in its waters of hydration, will also be eliminated. This process is very similar to Hess's law. One other thing that can be simplified would be the number of water molecules. And if I take a look, I see that there are 6 water molecules in the first equation, 24 water molecules in the last equation. So that's a total of 30 water molecules on the left. There's also 8 water molecules on the right. So if I have 30 on the left and 8 on the right, I will get rid of the 8 and change the coefficient on the left side to be 22. I don't see any other items that can be simplified, and so our full molecular equation would be 2Al plus 2KOH plus 4H2SO4 plus 22 waters yields 3 hydrogen gas and 2 alum. Now this process, in the lab handout, it asks you to complete this process with both the molecular equations and the ionic equations. So I have shown this process with molecular equations 1, 2, and 3. You will have to show this process as well as the one involving the ionic equations, which are numbered 1I, 2I, and 3I in the lab handout. So that takes care of the questions. We then get to the analysis part of the lab. For the analysis, you will start by using the full molecular equation for the synthesis of alum to determine the theoretical yield of aluminum, or of alum. And if I go back to this molecular equation a moment on the previous slide, the two important chemicals of interest would be the aluminum and the alum. And you should think about this in terms of stoichiometry. You started with approximately 0.5 grams of aluminum, and to figure out the theoretical yield, it really becomes a grams to grams problem. And so think back to chapter 3 when we did stoichiometry. Start with 0.5 grams of aluminum as your given, as your A, and solve for the yield of grams of alum. One thing to be careful of, when you are adding up the molar mass of alum, be sure you include the waters of hydration. I will tell you that the molar mass of alum, when you add it up, should be between 450 and 500 grams per mole. If you're not getting that, then double check your molar mass for alum. So starting from 0.5 grams of aluminum, you should be able to again determine the theoretical yield of grams of alum. And just another tip to make sure you're on the right track, the final amount of product of alum, depending on your starting amount of aluminum, should be somewhere between 5 and 10 grams. If you're not getting a number there, then you'll want to check with me. Once you have figured out the theoretical yield of alum, you should be able to use your data from the lab to get the net mass of alum produced. And you can use your final mass and your filter paper mass to figure that out. That will also be your actual yield. Once you have both of those, you should use actual and theoretical yield to get your percent yield. And one of the things that Dr. Hansen asks for in the analysis section is he said that he wants you to summarize the procedure used to produce alum. And it's probably easiest if you just start with the full molecular equation as your guide and state how each reactant was added and what happened to each product. He gives an example in the lab handout on the very last page. It says, an example, the KOH was added in step 1 as 25 milliliters of a 1.4 molar solution. That was added to the aluminum, and then that caused the aluminum to be oxidized. That would be one example, and you can include other examples to explain how each part of the process took place. The last part of Dr. Hansen's analysis section states your yield should have been less than 100%. Your discussion should, quote, speculate on the fate of the rest of the potential product, end quote. So you probably have less alum than your theoretical yield, so come up with some reasons why or an explanation of where it might be. Human error is not a good reason why your yield is low. There are definite sciencey procedural reasons why your yield should be less than 100%. So think about the process of the lab and the way the lab was performed as you think about your answer. And this lab definitely has a bigger analysis section than most, so make sure you've covered all these items, and then you can finish by writing a rerun conclusion. Feel free to revisit this presentation or listen to it more than once to help you keep track of all the things that you need to do in the lab. And of course, if you have questions, make sure to ask. Good luck.